Now I am going to discuss about digital voltmeters. So these digital voltmeters are broadly classified into three types. Those are ramp type digital voltmeter, integrating digital voltmeter, successive approximation digital voltmeter. Coming to the first one, and before going to the ramp type, we shall discuss about the applications of digital voltmeters. The applications of digital voltmeters are: digital voltmeter is used to know the actual voltage of the different components, and also different digital voltmeter is widely used to check if there is power in the circuit such as mains outlet, and if the voltage is known we can also calculate the current. So as well as calculating the voltage, you can also calculate the current, and also you can know the exact reading. While using analog meters, you might be skipping 1 or 2 points so that some readings might vary. So, but using digital voltmeters, you can know the exact voltage of different components. So these are some of the applications of digital voltmeters. Now we shall discuss about the ramp type digital voltmeter. So in this ramp type digital voltmeter, we are using, see here, ranging and attenuator. So in this ranging and attenuator, the input signal, input voltage is applied to the ranging and attenuator, so that the specific range which this voltmeter has to allow, so and which it has to stop, that is being decided in the ranging and attenuator block. So the frequencies which are in the specified range, the voltages which are specified in the given voltage range that are allowed, and that is given to the input comparator. That is given to the input comparator. For the input comparator, one input is coming from the ranging and attenuator, and the other input is coming from the ramp generator. So this ramp generator, you can use a positive going signal or a negative going signal. As of now here I am discussing about the negative going signal. The ramp generator is giving a negative going signal that is given to the one input terminal of the input comparator, and one is the input voltage for the input comparator. Here two comparators are used, one is the input comparator and the other one is the ground comparator. So this ground comparator, for this ground comparator, one input is coming from the ramp generator, that is negative going pulse, and the other input is grounded. The output of the ground comparator is given to the gate. This tells to when to stop the pulse. When to stop the pulse. That is zero reference. When the zero axis comes, x axis is received, then a stop pulse is produced. So this is given by the ground comparator. And when to start the pulse is shown by the input comparator. So both these pulses are given to the gate signal, so that from start pulse to the stop pulse, how much voltage is there, that is counted by the counter. After counting, this is displayed on the digital screen display here. And for refreshing the counter, that means when the reading is done, and if you want to check other reading, then a sample rate multivibrator will send a reset pulse to the counter, so that the counter will be reset. And also one more functionality of this sample rate multivibrator is it will produce the other again a negative going ramp signal or positive going ramp signal, whatever is required. It will give it to the ramp generator, so that next measurement can start. Okay, this is about the ramp type digital voltmeter. This can be explained by using the timing diagram now. So this is the timing diagram of the ramp type digital voltmeter. So as I told, this is the negative going ramp, this is the negative going ramp, and this is the input signal which is to be, this dotted line is the input signal which is to be measured. So when the ramp signal is less than the input signal, then a clock pulse is a start pulse is generated. So at that time the pulse has been started, and start pulse has been generated, and this will continue until there is a zero crossing. That means a zero pulse will be there, that is stop pulse is produced. So from start pulse to the stop pulse, how many number of pulses have been produced, that pulses are counted and displayed on the digital voltmeter screen. So this is the voltage which we have. Number of pulses indicates the how much apply voltage is there in the circuit. This is how you can measure the voltage by using ramp type digital voltmeter. Here I have used negative going ramp signal. Either you can also use positive going ramp also. Okay, this is about the ramp type digital voltmeter. And next one is the integrating digital voltmeter. So integrating digital voltmeter, here this works on the principle of voltage to frequency conversion. So whenever see here, this is the integrator here. This is the integrator, and parallel to that a capacitor is given here, and for this an input voltage is applied here. Input voltage is applied. So this input voltage is given to the integrator so that it will goes on adding the voltage. During this time, the capacitor here, which is connected in parallel with the integrator, gets charged. This gets charged, and till that time, whenever it reaches the charging, the voltage reaches a reference voltage. ER is the reference voltage. When E naught equals to the reference voltage, then a signal is produced to display on the digital frequency meter, and this is also fed to the pulse generator so that a feedback is given to the integrator, and it goes on integrating. Uh, for the present voltage, it continues to add to the output next voltage. So this frequency, whatever the frequency is produced, that is directly proportional to the input voltage. That can be discussed by using the timing diagram here. So here you can see this is the timing diagram. This timing diagram, this is the output at the integrator. So initially the capacitor is charging. During the time period, the capacitor is charging, and during the next cycle. So here you can see initially the capacitor is charging, and when the pulse is given to the pulse generator, it will completely discharge the capacitor in a short interval of time, in a short interval of time, so that T2, you can observe here, T2 is less than T1. T2 is less than T1. So that means initially the capacitor is charging, later the capacitor is discharging. So likewise again charging and discharging. So like this happens continuously. That means this goes on integrating. The voltage is goes on integrating, and it reaches ER. And whenever it reaches ER, then the pulse generator is triggered so that a pulse is produced, and during that the capacitor discharges very fastly, and again after discharging the capacitor is charging. During that the pulse will be constant. Whenever this is you can observe here the output voltage ER and T2 are constant. ER and T2 are constant. Only the input voltage is inversely proportional to the time period T1. Input voltage is inversely proportional to the time T1. So 1 by T1 indicates the frequency. 1 by T1 indicates the frequency. So the input voltage can be denoted in terms of the frequency. It is directly proportional to the frequency. So only in this diagram, here you have obtained the frequency. So that frequency, if you measure the frequency, from that you can measure the input voltage. So this is the integrating digital voltmeter. Next one is the successive approximation digital voltmeter. So successive approximation digital voltmeter, you can take an example here for this, a weight balance. So in that weight balance, on the one weight you will be placing the weight which is to be measured, and on the other one you will placing the weight stones. So that if the weight is more, then you what will you do? You can going on waiting, adding the weighting stones. Like that here in this successive approximation digital voltmeter, you will estimate some value. You will be estimating some value and you will be measuring the voltage. So first, whatever the input voltage which is to be measured is given to the input attenuator. So the functionality of this input attenuator is it will stop the unwanted inputs and it will allow only the required inputs. So that input is given to the sample and hold circuit. This sample and hold circuit is used to send the input voltage to the comparator. When the first input is being measured, then it will hold the signal for certain amount of time until the measurement is complete. When the measurement is complete, again next sample is to be sent to the comparator. So, like a sample, it will sample and hold. It is the sample and hold circuit. So here you are using a comparator here. For this comparator, one input is coming from the sample and hold signal, that is the input signal, and one is the previously placed output signal. This will compare both these two input and output voltage and it is given to the AND gate. So for this AND gate you are providing some delay also. Why you are providing this delay is if you want to wait for some amount of time for the measurement, then you need to place the delay circuit here. So from the output of the gate it is placed on the SAR, that is the successive approximation register. This successive approximation register contains the output that is placed on the display, that is digital output is displayed. To proceed for the next sequence, a ring counter has to be done. So this ring counter will increase the counter and also it will send the signal to the delay so that the calculation is appropriate. So after the successive approximation register contains the data that is given to the digital to analog converter. So here the digital data is converted to analog data and the analog data is given to the comparator. So this here only this comparator will process only the analog data. So now again the process repeats until the digital output, the completion of the input signal, until the processing of the input signal has been done. So here this process, but this process is will be time taking, but this will be very accurate. And here you are using a reference supply because a D2A converter requires a reference supply. And the start stop pulses are produced from the start stop multivibrator. This can be explained by using this example. See here, initially the MSB bit. MSB means most significant bit. That is the left side bit is called the most significant bit, and the right side bit is called the LSB bit. So initially the MSB bit is set to 1. It is set to 1. Now here the if the input voltage is greater than the output voltage, here Vi indicates the input voltage and Vd indicates the output voltage. If Vi is greater than V0 output voltage, then what happens is it will keep the MSB bit as it is and it will increase the next MSB bit. That is next MSB bit to 1. So output is 110 now. Likewise, if the input voltage is less than the output voltage, what it will do is it will make the MSB bit 0 and the next bit as 1 and 0. So likewise again it will proceed to the next process, that is again it will compare the input voltage to the output voltage. If the input voltage is greater than the output voltage, then it will set all the bits to 1 and next it will likewise if the input voltage is less than the output voltage, it will make the process reverse, that is 101. So this process goes on repeating until the output has been measured and it will display on the display of the successive approximation register. So this is the successive approximation digital voltmeter where you can see the digital output. So these are the different types of digital voltmeters which we can observe.